brief video, we will be exploring some applications to simple differential equations. So take note, this is just simple differential equations. So we have here one application for population growth. Population growth, we are looking at the variation in the size of the population over time. So if we let the population P be the number of individuals at a certain time t. So P is a function of t. P varies with time. And at a certain time interval, that's capital letter T. So if you have a time t plus capital T, which is our time interval, the population now is P as a function of t plus the time interval t. Whereas we can say that from our definition, simple definition lang, the expression becomes the number of individual added after as our time interval capital T is now the number of the P after the time interval T minus P before the time interval T. So if you have a longer time interval, the more individuals can be expected to arrive, and the shorter the time interval, the fewer the additions can be expected. So we can say that let's change the time interval. So let's define the time interval as NT. So we have our equation now derived from this expression. So you have P after the time interval capital T minus P before the time interval is equal to NT. Okay, we just change how we define the time interval. We just put an N there. Okay, so if we divide both sides by capital T, we will get this equation, which if this value approaches 0, so at smaller and smaller time intervals, this value approaches 0. We now have basically the definition for a differential, which is the limit as t approaches 0. Remember the differential definitions from the very, very basic differential class. It's not even differential equations, it's just differential calculus. The definition of differential calculus here. So this is the definition of a differential, and we can rewrite this expression as dp over dt is equal to n. So that is one of the basic expressions in population growth. Now let's have some cases. So case 1. Suppose that there is a change in the population that is due entirely to individuals being born. So as the time progresses, the fertility of the parents can also alter, so that there are more or even less of the offspring are born. So, you have now your N changing over time, because let's say N is your one of the factors that affects, or rather we here define N as one of the factors affecting your population growth. So another effect is introduced by the simple hypothesis that as more individuals there are at that time t, the more births are likely to occur. So of course, if there are more parents, there are more offspring, something like that. So now you have an N that is a function of both t and p, and p is also a function of t. So you have, it looks complicated, but it's just a simple, coming from the definition a while ago. So dp over dt, we just say that N is a function of both time and the population. And population is also a function of time. So do not be very, malito, in short, in looking at different expression, because we just here say that P is also a function of time, and N is a function of both time and T. So something like that. It's actually just a simple expression of what we define, or our definition of case 1. So when we rearrange this, we just randomly, not exactly randomly, we divide this one by P. So we just created an implicit solution of your differential. So you have 1 over P dp over dt, which is basically the specific growth rate definition. If you remember your microbial growth during exponential phase, this is your mu. Okay, so that is case 1. So case 1 is a bit complicated because you have 2 variables here, t and p. Whereas let's simplify this more. So in case 2, let's say that we just shorten the time interval. So that in this short time interval, there will be about twice as many births as in the interval of half its length. So we can say now that during a short time interval, the fertility doesn't change. So now our N is now basically just a function of your population. So just how many parents there are, the more offspring there are. So we have fertility doesn't change. The actual number of births at the time interval T can be expressed as simply N. Let's change our definition of N as NO, just to differentiate it from the first case. So N sub O as a function of T and time interval T, whereas your NO is a suitable constant. So we now have, since we are only, or rather the population is varying based on the number of parents there are, the initial value of the population, we just write the initial value of the population as NO. NO times P is a function of T times the time interval T. So we can rewrite the change, if you count the change in the population after the time interval and before the time interval. So basically the change in the population is equal to the number of our constant NO. So let's have our constant, and we pegged NO now as a constant, which is different from our case 1. Case 1, N is a function, it's not a constant. So now this is a simplification of case 1. So at a very short time interval T, we just look at the number of parents, and the number of parents is basically just the amount of the initial condition of the population, NOPT. So that's why it becomes NOPT. So you have a constant NO times the number of initial population there are before the time interval and times the time interval. So this is now our definition. And now we just divide it by T, and then we get the definition of a limit. So therefore, we have a differential equation defined such that you have your change. These are the change in the population over time, which is equal to the number of population times just NO. And we can now define NO as the specific growth rate. And this is based on our case. This is now a constant at any time interval or at any time T. So this is for case 2, which is a simplification of case 1. And this is, if you notice, this is your microbial growth equation. So the solution now for case 2, we just solve the equation. So we have your, since we can rewrite this as dP over dt is equal to NOP. And then we divide everything by P, and then we just separate the variables, and then you will get, separate the variables and integrate it, and then you will get this solution. P of T is equal to PO, initial population, times the natural logarithm raised to NO times T. Whereas your PO is the population when time is equal to 0. Actually, practice doing integrations, or rather, practice your math skills. Derive this solution using separation of variables, and then you get the solution for case 2. Now, case 3. So, case 3, we suppose that the population changes not only to the births, but also we need to consider the deaths, immigrations, and emigrations. So now, for any time interval T, the change in the population is brought about by several factors. We let from case 2, the births as basically NOPT from the initial population times, how many times people are giving birth from that population. And then we added additional factors, which is the deaths. We let the number of deaths be defined by a constant D sub O times, of course, how much, or the percentage of how much of the population, or the initial population you have that died. And then you have the people immigrating from outside. This is I as a function of T. Now, Now, the difference here is that our DO is a constant, but I is a variable. It's basically a function over time. So, or rather, a function of time, t. And same was the immigration. The number of people emigrating varies over time. So, you have another function, e, as a function of t. So, you have here the change in the population at our time integral t is basically reliant on the number of births occurring, the number of deaths from that population, so minus the number of deaths, plus the number of people immigrating, coming in from the outside, minus the people going out or emigrating from the area to another place. So, this case is more realistic when we talk about population dynamics. Well, for community of people, but for community of microorganisms, basically, we are just looking simply at the births, and if we want to consider the deaths, but usually just consider case 2 for microbial growth populations. But in the case of human population dynamics, these are some of the factors that we need to consider. And so we just divide everything by t, and then get the limit as t approaches 0. So you have your integral dp over dt, which is now, just simplify this one to get the number of deaths and the number of deaths and the number of births of a population. So which is a constant. So basically, it's a factor of people giving birth, and also a factor of the people giving birth, and also the factor of the original population that's dying. So you have NO and DO, these are constants, and then plus the function IT, which is the number of people immigrating from the outside, and minus ET, number of people that are coming in, rather going out of the place, so emigrating to the outside. So if you have INE, which is, if we set INE as dependent on the population as well, we will come up with what you call Verhel's differential equation. Actually, this is a more complicated topic, but I'll just simplify it. Basically, if you want to read more, you can look up in Verhel's differential equation, but I won't be including it so much. Okay, that's for population dynamics. Now, for drug administration, so this is more easier to, I think, this is more closer to home type of sample. So you have, when you administer a drug, so it forms a concentration in the body fluids. So this concentration diminishes in time through elimination, destruction, or inactivation. So as you can see here, this is the plasma concentration of a drug taken at different routes of administration. So you have oral transmission, intramuscular, not exactly transmission, administration, and then IV, intravenous administration. So you can see, at a certain time t, although there is, for the case of oral and IM routes, you increase first, the concentration increases first. That is because we are looking at the plasma concentration, and for oral and IM, they are not directly administered to the bloodstream. So here, the increasing part of the graph here is basically the absorption to the bloodstream, and then over time, the concentration goes down. So for IV, intravenous injections, it's almost instantaneous increase because you are directly inputting it in the bloodstream. And then you can see that over time, the root or the plasma concentration of your drug is diminishing. So the rate of reduction of the concentration is in most cases proportional to the original or to the concentration that you have. So based on that definition, since the rate of reduction is proportional to the concentration, we say that we can express that as a differential equation. So the change in the concentration over time, that's dC over dt, is proportional. Since it's diminishing, so you have a negative sign, it is proportional to your concentration of the drug, which is C function of T, because the concentration changes over time. So in order to have the proportionality constant, we introduced a value of tau. So instead of just we want to make it in this model, we want to have the proportionality constant as a reciprocal, so 1 over tau as the proportionality constant. So in here, this proportionality constant describes the rapidity at which the concentration falls. So if we have a higher tau value, that means the concentration falls rapidly. And that is the reason, that's also one of the reasons why it's in the denominator instead of just, why not we just write it as tau times Ct? Well, it's actually, as a proportionality constant, you can do this as tau Ct or C over T divided by our tau. But in this case kasi, we define our tau as the rapidity at which the concentration falls. That's why it's in the denominator. If you have a high tau, the change now becomes, we have your, or rather, when we say the rapidity of the tau, so we have a high tau, the drug, since it's a high denominator, so you have a very low now. This value becomes lower. So a high rapidity, the concentration falls faster. So you have this scenario. That is why tau is in the denominator. So high tau, the concentration falls immediately or at a faster rate. So if we get the solution for this differential, we have, well, of course, separation of variables. So apply separation of variables. When you are doing this, or looking at this lecture, get your pen and papers and try to solve this differential equation. So it's just a simple separation of variables and then integrate. You will get the solution as C is a function of T, CO, whereas this is the initial concentration at time T is equal to 0, and E raised to negative T over tau. So this is your solution to this diminishing model. So in this model, we can say that the drug never disappears completely from the body. Why? Because we have here a natural logarithm value. So we basically generate a graph that is asymptotic to your x-axis. So this is basically just a model. We know that it's not always true, but this is basically an approximation of the behavior or the phenomenon that we observe, and that's what a model is. It doesn't necessarily have to be very exact, but it can approximate the behavior of the system. And that's also one of the reasons where there are many models, there are many cases, there are many models that are continuously being developed, because they are improving upon previous models, because the previous models usually do approximations only. Okay, now since there is the drug never completely disappears according to this model, we now have a residual concentration. But this residual concentration, if we have at greater time, so after a very, very long time, the residual concentration can, since it's asymptotic, it's very close to 0 but not equal to 0, but it can be negligible. For all intents and purposes, it becomes negligible. So, notwithstanding this, the fact that some of the drug is always left is relevant when you have repeated doses, and which is the common practice. Of course, when you get sick and when you have, say, inflammations, when your doctor prescribes you antibiotics, of course you do not just get antibiotics a single dosage. You usually take it 2 times a day, 3 times a day, depending on what is prescribed by your doctor. The same goes for, say, chemotherapy. You do not just administer chemotherapy drug once. There are repeated administration of the drugs in order to destroy cancer cells. Actually, it's critical to do the repetitions at regular time interval. And actually, these types of models is very important in those scenarios, or in those dosage, or in those applications. So in common practice, drugs are administered regularly at set time intervals such that each dose increases the drug concentration instantaneously and in a fixed amount. So here you have your dosage numbers, and it is the initial concentration of the drug. So the concentration of the drug in your bloodstream, so after the, say it's the first dose, or even from the residual concentration if the drug is administered before, so it of course goes down over time. And then when you administered a new dose, the second dose of the drug, it shoots up immediately, but over time it still diminishes. And then another dosage, it shoots up again. So you have actually an oscillating type of graph. So as you can see, you have your the general behavior is basically increasing, or it seems to be increasing based on the number of doses. Actually, if we time the different intervals, we can now have your graph behave in such a manner that we want to have. So let's look closely at our graph. Now, suppose that at a certain time, initial time, TO, we have our residual concentration R1. So let's say that the drug was administered sometime before. And at a certain time, TO, we have the residual concentration of the drug R1. This is the residual concentration just before the second dose. So if we put TO as the time just before we administer the second dose, we can say that the residual concentration is equal to the initial concentration of the drug times the natural logarithm e raised to TO over tau. This is just applying the equation from here, whereas we just change C as a concentration of CT into R1 because we just change the definition of this concentration, whereas, or rather, we just define R1 as the concentration, the residual concentration just before the second dose. So basically, R1 is basically C, a concentration, a part or a point in the function, the concentration function of the drug. So you have R1. That's basically just how we define it. So R1 is the initial concentration from the very, very first administration, or rather just the first dosage, times the E, whereas here, the T sub O here is the time just before the second dose. So when we now administer the drug, so after, this is the residual, and then we administer the drug. So of course, this is basically just the concentration now of the drug in the system is just the algebraic sum of the dosage you applied, CO, and of course the residual concentration R1. So this is R1. So the residual concentration plus the dosage you apply, that's now the concentration of your drug in the system after the second dose. So now at a certain time interval between the second dose and the third dose, so after another time interval, so we define that time interval as 2T sub O. Of course, the concentration now falls again. So remember from our graph, so you have the residual dose, this is the T sub O, let's say this is T sub O, you administer the drug, and then this one is now C1. So this part here is R1. So administer the drug, that is C1, and then over some time, of course, some time elapsed, the drug is diminished in your system, so you have another value, R2. So another concentration, another point in the concentration function. And this is just before the third dose as R2. And so, continuing on with from before, so we just follow it. So this is, if CO is the concentration from the first dose, we just get C1 now is the concentration from after the second dose. C1, and then just apply the same model, we have R2. Or we can rewrite that since C1 is this one, so if we substitute it, we get this function. So that is now the residual concentration just before the third dose. Now, again, when we administer the third dose, we now have another C2. So the C2 this is the concentration of the drug after the third time you administer the dosage. So this is CO. CO is the dosage you administer. So it's consistent. Of course, when you're intaking drugs, you're not changing the dosage. Or we do not usually change the dosage. So you have CO and CO. So still added another constant CO. And of course, CO is added to the second residual, R2, the residual concentration just before the third dose. So we just get R2. So from our definition of R2, this is our R2. So we just substitute here, you get this value. This is now the concentration just after the administration of the third dose. Now, we repeat that as many times as you want, or rather as how many times your prescription tells you to do. So 7 times a day, so that's 2 times a day. For 7 days, you have 14 times, so you just do that repeatedly. So if we kept repeating that administration at our nth dose, so the nth dose is defined as the time n minus 1 times TO. So that's our nth dose. This is the time of the nth dose. So now our concentration now of our drug is continuing on from our pattern here, so we just CO plus times 1. This is from the first dose, this is from the second dose, from the third dose, so on and so forth until you get to the nth dosage. This one for the nth dosage. So you basically have a geometric series. And if we get the sum of this series, we get this amount. So remember, this is a geometric series, and the sum of the geometric series is this one. So and then we just multiply CO. So this is now the concentration after the nth dose. So then if you have the concentration after the nth dose, we also have the residual. So let's look at the residual concentration. The same definition goes. We have if you remember our residual dose, same. We can actually see another geometric series here. So if we have this geometric series, we get this value. So you have Rn CCO times E raised to T. So we just now have an added factor is above, because from the initial definition we have this value for that one. So okay, or we can just simply get this one and substitute it here on, since we define it as Cn minus 1, so just substitute. So you now have this equation. That is the residual concentration after the nth dosage. So this is your concentration, the concentration over time. So as you can see, there's a build up in the concentration. There's a build up in the number of doses as the dose increases. So you have an oscillating manner. So from this equation, however, although it looks increasing, it's steadily increasing from what you can see. But if we analyze our equation, this is our model. The concentration of the drug after n dosage, so we can say set n to infinity. And looking at this model, in here, it's basically, what is basically changing here is just the factor n. So as n approaches infinity, we have e raised to negative infinity times t. So you have, if we set this one as infinity, our exponential then, since it's a negative exponent, it then decays to 0. So our numerator is diminishing steadily. So that means if we, as the n gets higher and higher, the value of n gets higher and higher up until infinity, this entire exponential, this term becomes 0. And so we now have, after infinite dosage or limitless or how many number of dosage, we can simplify this model such that we get this one. So CO over 1 over E times TO tau. And since if we set n as infinity, we get m. And this is basically the limit. So this is a limit of the concentration. So basically, even through repeated dosage, the concentration of the drug in the system will only reach a certain limit and will not exceed that limit, no matter how many times you apply the dosage. So this limit can be used as a good estimate for the concentration immediately after dosing them. Because of course, if you look at our graph, this is our limit. So let's say this is just basically the limit. This is attained, the limit is attained every time we administer the next dose. So just after administrating the next, so that is, we hit the limit. So we can now simplify, instead of getting a C after the 4th dose, we calculate C sub 4. We can just, for every succeeding dosage, we can just use this Cm value to get the concentration after each dose. So although it's not exact, but it's a good enough estimate. So when our NT is greater than or much greater than 1, so actually we usually reach the limit after 5 doses usually. So that's just how it is when you do administration. So the Cm, the limit can be reached in just only a few doses if the time interval between doses is high. If you have a high time interval, the limit is reached immediately. So in a similar manner, you have a residual concentration R just before the dose. So if we have a limit, the upper limit, we hit upper limits in administering doses, we also have a lower limit. And we can define that lower limit as R. And R from the definition of the other R's, how do you define the other R's? The other R's is defined as this one. So if we define the other R's, or rather this is the definition of the other R. So if your R is equal to Cm e raised to, so on and so forth. So this is now our R. Cm e raised to T0. So we just rewrite this one and as this one. So from this equation, if we analyze this equation, our residual concentration after every dose. So the R now can be an estimate of the residual concentration after every dose. So no need to get R1, R2, R3, R4. So we'll just use R for almost every R after, say, the third dose. So we have the R. So our residual concentration, the amount of drugs left in the system, becomes smaller if we have a very large value of NT raised to tau. That means if you have large interval between dosage, the residual concentration drops significantly. Or even if you have a high tau, that means the drug decays or is destroyed, or not exactly destroyed. Well, it disappears rapidly from the system. So you have smaller R. So we now have a trade-off between keeping a residue after a certain level and reaching Cm in a few dosage. The thing here, the reason why we need to look at the R's, the limit, the lower limit, and the upper limit is because, for example, in drug administration, drugs are, although it helps us, it helps you get well, they can be poisonous if taken too much. So we do not want to exceed the limit. And we usually set the limit as the safe limit. So we cannot exceed the safe limits, Cm, with our dose. But at the same time, we do not want the concentration of the drug to fall below a certain threshold. Why? So let's say, for example, antibiotics. So in the case of antibiotics, let's say in this case, this is the graphical representation of our limits, upper and the lower limits. Say in the case of your antibiotic drugs, if we have a very high dose of the antibiotic drugs, that can also affect the cells in our body. So it can be toxic in a way. At the same time, it can also affect the microbiota that we have in our intestines. So it will be actually detrimental to our health now if we exceed the Cm. At the same time, if we fall below a certain threshold value, such that if the drug concentration falls below the R, the threshold value that we wanted, okay? Now, the antibiotic now, since it's very small amount of antibiotic, it becomes ineffective in combating the pathogenic bacteria. And what happens? The pathogenic bacteria now will develop a resistance. And we do not want that because it will become very difficult. That's actually one of the reasons why we need to, antibiotics are prescription drugs and we do not want them to use willy-nilly. So you have to maintain proper dosage and times of administration such that you do not exceed the upper limit so that the drug won't be toxic to you. At the same time, you do not want the concentration to fall below the residual concentration such that your bacteria, the pathogen, can develop resistance. Now, the thing here is, based on our model, we have a trade-off. So if we increase the dosage, CO dosage, we can keep the R, the lower limit, from falling too low. However, if we increase the initial dosage, we can exceed now the upper limit. So that's one of the things to consider. And then another thing, if we administer the drugs, if we do not, say, instead of playing around with the initial dosage, we just play around with the time interval. If we have a large time interval between drugs, we usually immediately falls below. It can fall below the lower threshold value. So the R value becomes very low. So it becomes difficult. Although we can reach Cm immediately during the second dose, we reach down the Cm. If we have large time intervals, we can fall below the lower limit. So that's one of the things that we need to consider. So let's say, for example, a drug is available in doses of M, a variable M milligrams, which raise the blood plasma concentration on an average adult by 10 milligram per liter. So once in the blood plasma, the drug concentration decays according to our model. So our model here, this model. Where is it? Okay, this model. So the drug decays according to our model. So you have your tau as 4 hours. So tau is an intrinsic constant. It's a constant intrinsic to the nature of the drug and how that drug is processed in the system. So basically how the drug is processed or decays in the system. So the tau is 4 hours. So the health regulations require that the concentration must never exceed 15 milligrams per hour. Now, what is the shortest safe time interval at which the doses can be given regularly? So in here, at each dose, we have an increase of 10 milligrams per liter. And then it decays at a certain rate of tau is equal to 4 hours. So we should not exceed 15 milligrams. And the next question is, what's the minimum concentration if doses are given at this time interval? So basically, this is just a simple substitution. We analyze what we are given. The CO, the dosage concentration, 10 milligrams per hour. Our limit is 15 milligrams per hour. And our tau constant is 4 hours. So we just get to find the shortest time interval, we just immediately proceed to CM. So we just substitute CM. We just substitute the variables and get TO. TO is the time interval. So we end up with a value 4.4 hours. And to get the minimum concentration, the residual concentration, usually we achieve that immediately after the second dose. It's always the lowest concentration. It's immediately after the residual concentration immediately before the second dose. That's the lowest point there is. And that is what we will do to get our R. So our R now is 3.3 milligrams per liter. Just a simple concentration. Okay, so that is for drug administration. This is our reference, and you can practice more on this one.